Okay, good morning, everybody. I'll be taking organic chemistry for today, and this is one of the topics many students find very challenging in JAM exam. Understanding organic chemistry gives you 30% readiness for chemistry in JAM examination. So let's talk about organic chemistry. Like we have in the board, organic chemistry is the study of chemistry of carbon, with the exception of simplest inorganic compounds like carbon 4 oxide and the triazocarbonates. Example, you could see them on the board, CO32 minus. Now, whenever you have the word organic talks about things that occurs in nature. Do you understand? So it's a chemistry that occurs naturally. So it does not include inorganic compounds that can be synthesized in the laboratory. Okay. Then also, organic compounds could be divided into two major classes, two important classes. The first one we have the aliphatic organic compounds. The aliphatic organic compound talks about straight chain hydrocarbons and also talks about closed ring compounds. You could look at this structure here, ethane, you could discover that this is more of a straight chain because the carbon to carbon are linked in a straight manner. Do you understand? And it will interest you to know that the ability for carbon to be bonded to another carbon atom in organic chemistry is called catenation. I think I will have to write that on the board. It's called catenation. JAM usually asks this in our examination. Catenation is the ability for what? For carbon to be bonded to another what? Carbon molecule what? In an organic what? Compound. We also have cyclopropane. Cyclopropane also belongs to the class of organic compound we call the aliphatic compound. So aliphatic compound they could be straight chain, they could also be in the ring format, okay? Then the second class of organic compound we have is the aromatic compounds. The aromatic compounds we have on the board, we say these are compounds with non-delocalizable orbital. When we say non-delocalizable orbital, it means the orbital are not, or the double bond present are not placed or peculiar to just one position. If you watch the structure of benzene, you can see the double bond is here. We have 3 pi bonds, right? And 6 pi electron. You can see I have a double bond here, but in this next resonance structure, the double bond is at this position. The word delocalized means the pi bonds are free. They are free to move around, the orbiter. Do you understand? Okay. Okay, now we look at the characteristics of organic compounds. So when we talk about the characteristics of organic compound, we're talking about the things that are peculiar to organic compounds. And the first characteristics of organic compound is that they are covalent in nature. When we say they are covalent in nature, it means the bond in most organic compounds is covalent bond, right? And because they are covalent in nature, they are immiscible in water because covalent compounds their gases at room temperature. When we talk about room temperature, we're talking about their natural existence. Okay, so they are immiscible in water, with the exception of polar organic compounds like alcohol. Alcohol is very soluble in water, yet it is an organic compound. The reason is because alcohol, like for instance, ethanol, can be broken into C2H5 plus OH minus. The are key components being These are key components being C2H5 is partially positive, and this OH, that's the hydroxy ion, is negative. So in this case now, it can dissolve in a polar solvent like water because water has what? Two components. You have the OH minus and you have what? The H plus. Maybe I will illustrate it for you to see it. For water, I have OH minus, right? I also have H plus. So when we say a substance is polar, it means it has both the positive and also what? The negative side, right? So water is a polar solvent because it has OH minus on the negative side and H what? Plus on the positive side. Similar thing happens to what? Alcohol. But organic compound, generally they are what? They are not soluble in water. They are immiscible in water. You understand? With the exception of what? Compounds like alcohol. Okay? Then we talk about hydrocarbons. Hydrocarbons are compound that contains only carbon and hydrogen. Many students normally make this mistake. Compounds containing aldehydes, ketone, like for instance, you have formalin, they are not hydrocarbons because they contain other atoms beside hydrogen and carbon. So the only hydrocarbons we have are the alkanes, and alkynes. They are the only hydrocarbons we have because they contain peculiarly what? Carbon and what? Hydrogen. And one specific thing about this hydrocarbon is that they are mainly found in what? In petroleum products, crude oil. Like the kerosene you use at home, you understand, is known to be called paraffin. Do you understand? Okay. This man can be called, it has another name we call paraffin. The alkanes can be called paraffin. The alkanes can be called olefins. Okay, so alkanes and alkynes, they are what? They are hydrocarbon because they contain just hydrogen and carbon in their what? Their parent structure. Okay, we'll talk about the concept of functional group and substituents. If you're able to understand what functional group is all about, I tell you, your understanding about organic chemistry will be much, much more interesting. Functional group refers to a bond or group of atoms that is peculiar to a particular organic class of compound. It's already on the board. Functional group refers to what? A bond or group of atoms peculiar to a class of organic compound. You could see here, I have a single bond. Which class of organic compound has single bond as a functional group? The alkanes. You have methane, you have ethane, the likes of butane, propane, down to wherever you want to stop. You discover that you see what? You keep seeing a single bond. Then for the alkanes always have what? Double bond as their what? Functional group. The alkynes have what? A triple bond as what? Their functional group. And one specific thing about this functional group is that it determines the chemical property of a particular class of compound. It determines what? The chemical property of what? A particular class of organic what? Compound. Why, when you talk about substituents, substituents are atoms that are attached to an organic compound. They are atoms other than that particular class of compound that are like an attachment. For instance, now we have on the board, we have chloroethane. Normally, what should be here? If I remove the Cl here and I have my hydrogen, I won't call this man a substituent. But if I remove hydrogen and put Cl, I can call this chlorine a substituent because it is more of an attachment. Do you understand? To this particular class of organic compound. And one importance of substituent and functional group is that something that will make you understand it better is that just try to visualize, red hot oil and granite oil. If granite oil is red hot and palm oil is red hot too, and you just put a tip of water inside, you discover that you get a sharp sound that, oh, you might find it so, irritating, right? Yes. So functional group is what is responsible for that sound. For instance, like I said, you have red oil, palm oil, you have granite oil, and both of them are red hot. If you drop water inside, you hear a sharp sound, right? A shrinking sound. So functional group, you can be liking that water, red oil and granite oil has what? The same functional group. I'm just giving a hypothetical illustration. The ability to produce that sound can be likened to them having what? The same functional group. Why there are differences in color. Red oil is red, right? Granite oil is like a bit brownish, true of us. Okay, so there are difference in color. When we're talking about organic compound, what accounts for that difference in color is their what? Substituent. So substituent in a nutshell, it affects the physical property of organic compound, while the functional group affects the chemical property of that particular organic compound. Okay. Hey. Now we talk about homologous series. I believe this is not your first time of hearing about homologous series. So this refers to a series of organic compound in which each member differ by a CH2 group. In organic chemistry, we have different homologous series. We have alkane, we also have the alkanes, we have the alkynes, we also have the alkanes and the like of them. And each of these class of organic compound, they have particular formula that can be used to derive each component member. So let's start from talking about the alkanes. But before I talk about the alkanes, there's something I want you to know that is very important. In homologous series, each of the member differ by a CH2 group. Each of the member what? Differ by what? A CH2 group. It means that if you get the first class of any organic compound, you can just keep adding CH2, you keep getting the subsequent classes and the likes of them. So because they differ by a CH2 group, they also differ by a relative molecular mass of 14. Because the molar mass of carbon is 12 and the molar mass of hydrogen is 1. But we have 2 hydrogen here, so it is 2 times 1. So we have 14 gram per mole. JAMB may also ask you that which of these is not a characteristic of what? Homologous series. They will put the first option A. They differ by a CH2 group, which is correct, it's not on the board. B, they differ by a molar mass of 14 gram per mole. You've seen that on the board. So you could be able to eliminate your options when you see this in your JAMB examination. So talking about the alkanes. Alkanes are a class of organic compounds with the general formula of CnH2n plus 2. This formula you're seeing here is the formula that is peculiar towards the alkanes, and you can use it to derive all the members of the alkanes. Okay, they are also known as what? Paraffins. Alkanes can be called paraffins. They usually end with the suffix ane. I believe most of you are waiting for the nomenclature, of which I'll start looking at how to name the alkanes right away. Now, looking at the general formula, I want to derive other members of alkane, where n is equal to 1, because the formula says CnH2n plus 2 as the general molecular formula for what? The alkanes. So for instance, where this n is equal to 1, can you see the 1 here? You can see this 2 here, right? I replaced my 1. You can see the 1. I just did substitution. Plus 2. I have C1, because you don't write 1 in chemistry. So this is C. 2 plus 2 is what? 4. It means I have CH4. So the first member in the alkane family is called the methane. It's called the what? Methane. Now, there are Latin or Greek prefixes that enables us to name organic compound. The moment you see just one carbon in any organic compound, you use the word. You could see 1 carbon, we use met. If you see 2 carbon, you use et. If you see 3 carbon, you use prop. If you see 4 carbon, you use but. Now, what becomes the suffix depends on the class of organic compound you're talking about. So in this case, we are talking about what? We are talking about the alkanes. The alkanes. In other words, all of the organic compounds we are going to be naming under this category must end with the suffix ane, attached with either et, met, prop, but, depending on the number of carbon that is attached. Now, where the first member is CH4, which is methane, I've explained to you. If we want to get the next member, instead of we using this formula, that is the general formula for the alkanes, there is no point of we making use of it again. We just keep adding CH2, because alkanes belong to the homologous series. Alkanes also belongs to the homologous series. All class of organic compound belongs to what? Homologous series. And by the rule of homologous series, it says that what? Each member differ by what? A CH2 group. So I can just add CH2 to CH4. I will get the next member. Let's check it out. CH4 plus CH2. 1 carbon plus the other carbon. Can you see C2 here? 4 hydrogen plus 2 hydrogen. Can you see I'm having about, okay, so this should be C2H6. Do you understand now? So let's check it out. 1, 2. You can see the 2 carbon, right? Then 1, 2, 3, 4, 5, 6. You can see the 6 hydrogen. And one rule I want you to understand in organic chemistry is that in organic chemistry, 4 bonds must always surround carbon, because carbon is tetravalent by nature. When I say carbon is tetravalent, this is what I mean. If I draw, carbon, the atomic number for carbon is 6, right? It means that if I'm to draw the electronic configuration, carbon will take, you can see this, carbon will take 2 electrons in the first shell. It will take 1, 2, 3, 4. So writing it that I will have something like this. Please watch. I will have something like this, 2, 4. Right? Now, looking at this, the valence electron is what? Is 4. So it tells you that carbon is tetravalent. When I say tetravalent, it means 4 bonds must surround what? Carbon. So if you look at the first one, you can see that 1, 2, 3, 4. 4 bond is attached to carbon. So the moment you're writing any inorganic chemistry structure, always make sure that 4 bonds surrounds what? Carbon. And also, one bond must also be attached to hydrogen. The reason is because hydrogen is just the first element, right? So if I draw the electronic configuration, I just have only what? One electron. So in that case, hydrogen is what? Monovalent. It means just one what? Bond must be attached to hydrogen. So you can see, look at all the structure, you see one bond attached to hydrogen, right? This explanation will be very, very useful when I start talking about what? Alkanes. Okay, now let's keep getting the next member. So if I add CH2, if I add CH2 to ethane, the one I have here is ethane. So if I add CH2 to it, I will have C3H8, right? Okay, because C plus C2 give me C3, while 2 plus 6 gives me what? 8. Now, to draw the structure, I will draw my 3 carbons first. 1, 2, 3. Like I told you, that 4 bonds must be attached to carbon from what I illustrated previously. I can see 1 bond there. 1, 2, 3, 4. 1, 2, 3, 4. Can you see the 4 bond? 1, 2, 3, 4. 4 bonds is attached to this carbon. You can see it, right? 1, 2, 3, 4. You can see 4 bonds attached to all the carbon. You can now start placing your hydrogen. It becomes much more easier this way. The moment you count it, everything will be equal. Let's check it out now. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hydrogen. For the carbon, we have 1, 2, 3. You can see it now, right? Then also, if I still want to get the next member, instead of me making references to this formula, I can just keep adding what? CH2. Because alkanes also belong towards the homologous series. So to get the next member, we have C4H10. So if I want to draw the structure of C4H10, to make it much more easier, how many carbons do you have there? You have 4 carbons. So first of all, outline the carbons you have. 1, 2, 3, 4. And make sure that 4 bonds are attached or surrounding each of the component carbon atom. I could see 1 bond there, so 2, 3, 4, right? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Just attach your hydrogen. The hydrogen will then perfectly fit into the structure. Okay? So if you make a head count, you discover that you're having what? You're having 10 hydrogen and what? 4 carbon. So how many carbon is here? We say it's 4, right? So when it's 4 carbon, what do we have? We use the word but. So this becomes butane. I didn't name the previous one. We have 3 carbons, so it's called what? Propane. It's called propane. Okay, in the comment section, you can tell me how many hydrogen hexane we have and how many hydrogen heptane we also have. You can do that in the comment section. Okay, then now let's look at further way on how we can be able to name compounds involving alkanes. Now we have a particular class of organic compound on the board. Now one of the first steps to be able to name this compound on the board is that originally, if I remove this chlorine and put hydrogen, right? This 1, 2, 3, 4, right? This is just 4, that's but. So I call this what? Butane, right? So the first step is that always identify the longest chain. So this compound originally, what should come to my mind is what? Butane. I will just write my butane and put it somewhere. Okay? Then I remove my hydrogen. I put my Cl. So this Cl, like I explained previously, is what? A substituent because it is more of an attachment. So if I start counting from either the right or the left, where will I meet this substituent? Because this substituent is more of like a stranger in this organic compound. So it's very important and validatory we identify it, okay? So from the right or from the left, where do you think you will meet this substituent easier? Is it from the left? No. Because from the left, if I start counting, I will have 1, 2, 3. Right? But if I start counting from my right, I will have 1, 2. So I will have this chlorine at what? The second carbon what? Position. So whenever you have halogens like chlorine, fluorine, bromine, iodine, and all that, we use the word chloro, bromo, iodo. I think I will have to write that for you to see it. We use chloro, bromo, fluoro, iodo, and the likes. Okay. So in this case now, the chlorine is at what? Carbon what? 2 position. So we'll say 2 chloro, then we'll just put, because butane is the parent name, right? So we'll say 2 chloro, 2 chloro what? Butane, 2 chlorobutane. This becomes the name of the structure. But I will advise you to notice that we use hyphen to separate number and alphabets. In organic chemistry, why name it? Many students do make this mistake. We use what? Hyphen to separate what? Numbers and what? Alphabets. Why we use comma to separate in the case where we have 2 numbers. Take for instance, I have about 2, let's say dibromobutane. I will use comma to separate the 2 numbers. But before I get to an alphabet, I will use what? I must use what? Hyphen. Okay. We've known the first one. Then for the second one, we have a compound here on the board. You can see I'm correcting the mistake I made because I know that 4 bonds must be attached to what? Carbon. You can see it here. So 1, 2, 3, 4. Okay? Now looking at this structure, for we to be able to know the name of this organic compound, the first step is to identify the longest chain. The longest chain in this case is the parent chain. Now, one way that will enable you to identify the longest chain is that if, for instance, this was a pipe, right? If I pour water inside this pipe, say water will move in this direction, the water will keep moving. It will keep moving. At this point, the water will split. It could either split here or it will move to this position. So the point in which water is retained maximally can be likened to the what? The longest chain. Do you understand? But in this case, water will reach this position and this position at what? The same time. So you could use like this as the longest chain, or you can either use like this as the what? Longest chain. Do you understand? Okay. Okay. Now, let me use this way as the longest chain. Okay, let me just make it a straight chain. So how many carbon do we have here? We have 1, 2, 3. So the longest chain is propane. The first step always starts with identifying the what? Longest chain. Now, in this longest chain, you discover that at that point where water flows away from the straight chain, it tells you that there is an obstruction. It means that there is a substituent there. Okay, so in this case now, this man is the substituent. This man is also a substituent because it is not originally part of this organic compound. Okay, so this substituent here is what? Bromine. But bromine is at which position? It's at position what? 2. Because I start from my right or from my left, I'll meet both bromine and this other substituent called methyl. I'll meet them at position what? 2. Methyl, propyl, butyl, they belong to an organic class of compound we call the alkyl. We call them what? The alkyl. This alkyl, they always occur as what? As substituents. They are atoms in which they've lost just one hydrogen, what? Or let me say they are class of organic compound that have just lost one hydrogen atom. This is what I mean. To draw the structure of methyl, this is methyl. This is methyl. This is methyl. CH3 is methyl. But organic compound, you can't have just 3 bonds surrounding what? Carbon, right? You can see just one bond attached to hydrogen. But carbon here, you see the bonds are not complete. So for that singular reason, alkyl, they don't occur on their own. They always occur mainly as substituents attached to other class of organic compounds. Do you understand? So in this case now, we have methyl attached towards this class of organic compound we call it what? Alkane. So since we've identified the longest chain to be propane, we go for the substituents. We have what? We have bromine. This is carbon 2. Okay, let me start this way. This is carbon 1, this is carbon 2, this is carbon what? 3. So bromine and methyl is at what? Position what? 2. But which one do you think will come first? Of course, bromine will come first because when you follow it alphabetically, you meet B before what? M. So the name of this compound becomes 2-bromo. I will then put another hyphen. not a comma because I want to attach a number. So 2-bromo, 2-methyl-propane. That's the name of this structure. 2-bromo, 2-methyl-propane. Okay? Now let's look at this one. Now let's name the third compound. Maybe you could try this, you could just pause the video and try this particular compound and see if you're going to get it. And keep the name of this answer in the comment section. Okay, but let me still do it actually. Now, looking at this particular compound here, let's count. I have 1, 2, 3. For you to be able to identify the longest chain in this compound, just give a kind of hypothetical instance in which if water was to be poured from this carbon, water will flow in this direction. The water will be flowing, to be flowing gradually. At this point, there will be an alteration. At this point where the water will split, it tells you there is a substituent there. So in this case, water could either flow like this and still continue like this. So if water was meant to flow this way and this way, which point will retain more water? Water will retain more at this position because water will flow like this, 1, 2, 3, and it will flow this way. So this point will retain more water than 1, 2, 3. Do you understand? So this is 1, 2, 3, 4. Water will flow in this channel. So this man can be likened to the what? Longest what? Chain. So let's count how many carbon we have there. We have 1, 2, 3, 4. We have what? 4 carbon. So the parent name is what? Butane. Okay? The parent name is butane. Then now looking at the second carbon, if you start counting from your left position, 1, 2, you discover that this is carbon 1, this is carbon 2. We have methyl as a what? Substituent. Why do I say this is a substituent? Because if water was to flow, I'll experience a deviation at this position. Water will flow like this. Water will not stop here. It will also come down this way. So this man can be likened to a straight chain in as much as it is bent. Do you understand? So in this case now, this substituent is at position what? 2. So we'll say this is 2-methyl butane. Because of the video, if there's any part you aren't, really okay with, you couldn't understand properly, you could reach out to us on the comment section, okay? And if you also need further assistance in organic chemistry, prior to your JAM exam, okay? So the link is provided in the comment section. You can reach out to us via our bio. Thank you.